Hello, my name is Paul Geyer, and I'm here to chat with you today about energy efficient HVAC controls. This is what I'll be talking about today, sort of the chapters in the book, if you will. By way of introduction, this is just a little bit about me and what I've been doing for the last few decades. I got registered in a few different things along the way, but I'm basically a mechanical engineer and have done a lot of HVAC design over the years. This discussion covers automatic temperature and humidity controls, space pressurization controls, safety controls, and energy monitoring and central supervisory control systems. A complete automatic control system must be designed by an HVAC controls design engineer with experience in designing systems of this type and complexity. Commissioning plan must be submitted to and approved prior to the commissioning of the control system. The final product shall be complete, reliable, and fully functional, maintainable, fully integrated, addressable control system that has been properly designed, installed, and commissioned. In existing facilities, the design shall be integrated and interfaced into the existing control system so that the new equipment and conditions can be controlled and monitored, similar to the existing controlled equipment. Compliance is recommended with Section 104 of the Energy Policy Act of 2005, which requires that Energy Star designated products be employed. The control system shall be a direct digital control DDC system reflecting the latest technology that has been widely accepted by the control industry. DDC systems shall be electronic only. Pneumatics shall not be allowed except in instances when the existing controls absolutely require that the new controls be pneumatic. The system shall be complete and suitable for the HVAC systems to be installed. The DDC system shall be compatible with any existing systems in the facility or shall be able to completely and seamlessly interface with the existing Central Control and Monitoring System CCMS network. All control points, including the VAV controllers, shall be fully compatible with the CCMS, allowing complete monitoring, control, and set point adjustment of all points and VAV terminal unit controllers from the CCMS host. Outside air quantity to each air handling unit shall be automatically controlled at a volume to meet the requirements of ASHRAE Standard 62. Typical points to be monitored and controlled include for air handlers, leaving air temperature, entering chilled water temperature, leaving chilled water temperature, entering hot water temperature, leaving hot water temperature, temperature and humidity in each zone, fan speed indication, filter differential pressure, supply air quantity, and outside air quantity. For central plants, chiller on-off for each chiller, chilled water temperature in and out, chiller status, boiler on-off, each boiler, hot water temperature in and out, boiler status, steam, hot water heat exchanger, water temperature in and out, pump on-off indication, each pump, cooling tower fan speed, condenser water temperature in and out, steam pressure, and steam temperature. For variable air volume systems, the VAV zones through the VAV unit controller, zone temperature, zone primary airflow, supply and exhaust volumes, zone temperature set point. Alarm printouts, chiller failure to start, air handling unit fan failure, zone space temperature rise to 5 degrees above set point, chilled water rise 5 degrees above set point, hot water fall 5 degrees below set point, zone relative humidity 5% above set point, pump failure, water on floor of mechanical room, laboratory fume hood sash position, and hood alarm condition where fume hoods are installed. Other points to be controlled: start and stop for chillers and chilled water pumps, reset chilled water temperature, start stop boilers, hot water pumps, reset hot water temperature, start stop air handling units, start stop exhaust and supply fans, set point adjustment all controllers with set points, enable disable economizer cycles, set point adjustment for all VAV zones. The following codes and standards should be observed and applied. ASHRAE 135, a data communication protocol for building automation and control networks. Underwriters Laboratories UL 916, Energy Management Systems, NEMA 250. Enclosure for electrical equipment, NEMA ICS 1, General Standards for Industrial Controls. NFPA 45, Fire Protection for Laboratories Using Chemicals. NFPA 90A, Standard for the Installation of Air Conditioning and Ventilating Systems. And NFPA 70, the National Electrical Code. The control system design submittals shall include complete control system drawings, complete technical specifications, and commissioning procedures for each control system. As a minimum, the following documentation shall be required for review by the owner: HVAC control system drawings. Each control system element on a drawing shall have a unique identifier. The HVAC control system drawings shall be delivered together as a complete submittal. HVAC control system drawings shall include the following: drawing index, HVAC control system legend, valve schedule, damper schedule, control system schematic and equipment schedule, sequence of operation and data terminal strip layout, control loop wiring diagrams, motor starter and relay wiring diagram, communication network and block diagram, DDC panel installation and block diagram. The HVAC control system drawing index shall show the name and number of the building, state, or other similar designation and country. The HVAC control system legend shall show generic symbols in the name of devices shown on the HVAC control system drawings. The valve schedule shall include each valve's unique identifier, size, flow coefficient C sub V, pressure drop at specified flow rate, spring range, actuator size, close-off pressure data, dimensions, and access and clearance requirements data. The damper schedule shall contain each damper's and each actuator's identifier, nominal and actual sizes, orientation of axis and frame, direction of blade rotation, locations of actuators and damper end switches, arrangement of sections in multi-section dampers, and methods of connecting dampers, actuators, and linkages. The damper schedule shall include the maximum leakage rate at the operating static pressure differential. The damper schedule shall contain actuator selection data supported by calculations of the torque required to move and seal the dampers, access and clearance requirements. The HVAC control system schematics shall show all control and mechanical devices associated with the HVAC system. A system schematic drawing shall be submitted for each HVAC system. The HVAC control system equipment schedule shall be in the form indicated. All devices shown on the drawings having unique identifiers shall be referenced in the equipment schedule. An equipment schedule shall be submitted for each HVAC system. Sequences of operations shall be submitted for each HVAC control system, including each type of terminal unit control system. A complete sequence of operations shall be included on the drawings along with a schematic control diagram for each typical system. The sequence of operation and schematic control diagram shall specifically cover the following items and others as the project requires. refrigeration compressor control, refrigeration system protective devices, chilled direct expansion and hot water control, water coil or evaporator control, temperature and or humidity as required, cooling or air-cooled condenser control, air handling unit control with protective devices, individual unit control, motor interlocks with system starting and stopping instruction, all thermostat, humidistat, and protective device control settings. The HVAC control system wiring diagrams shall be functional wiring diagrams which show the interconnection of conductors and cables to HVAC control panel terminal blocks and to the identified terminals of devices, starters, and package equipment. The wiring diagrams shall show necessary jumpers and ground connections. The wiring diagrams shall show the labels of all conductors. Sources of power required for HVAC control systems and for packaged equipment control systems shall be identified back to the panel board circuit breaker number, HVAC system control panel, magnetic starter, or packaged equipment control circuit. Wiring diagrams shall be submitted for each HVAC control system. A list of service organizations qualified to service the HVAC control system shall be provided. The list shall include the service organization name, address, technical point of contact, and telephone number, and contractual point of contact and telephone number. The HVAC control system equipment compliance booklet shall be provided. It shall consist of, but not be limited to, data sheets and catalog cuts which document compliance of all devices and components with the specifications. The equipment compliance booklet, ECB, shall include a bill of materials for each HVAC control system. The bill of materials shall function as a table of contents for the ECB and shall include the device's unique identifier, device function, manufacturer, and model part catalog number used for ordering. The performance verification test procedures shall refer to the devices by their unique identifiers and shall explain step by step the actions and expected results that will demonstrate that the HVAC control and LFH exhaust systems performs in accordance with the sequence of operation and other contract documents. An outline for the HVAC control system training course with a proposed time schedule. Approval of the planned training schedule shall be obtained from the owner at least 60 days prior to the start of the training. 3 copies of the HVAC control system training course material 30 days prior to the scheduled start of the training course. The training course material shall include the operation manual, maintenance and repair manual, and paper copies of overheads used in the course. The HVAC control system operation manual and the HVAC control system maintenance and repair manual shall be provided for each HVAC system. Summer and winter space or zone humidity control shall be provided only on a space-by-space or zone-by-zone basis and not for the entire central ventilation system unless required for project-specific humidity requirements as stated in the project criteria. No control shall be provided for dehumidifying spaces to below 50% relative humidity or for humidifying spaces to greater than 30% relative space humidity unless required by project-specific criteria. Simultaneous heating and cooling, which controls comfort conditions within a space by reheating or recooling supply air or by concurrently operating independent heating and cooling systems to serve a common zone, shall not be used except under the following conditions. Renewable energy sources are used to control temperature or humidity. Project-specific temperature, humidity, or ventilation conditions require simultaneous heating and cooling to prevent space relative humidity from rising above special space relative humidity requirements. Project-specific building construction constraints as established in the project criteria prohibit installation of other types of HVAC systems. All supply, return, and exhaust ventilation systems shall be equipped with an automatic and manual control of fan operation to shut off the fan when ventilation is not required. To prevent introduction of outside air when ventilation is not required, these systems shall also be provided with manual, gravity-operated, or automatic control dampers for outside air intake and exhaust or relief. Systems that circulate air shall be provided with minimum outdoor air damper position control to ensure that the minimum amount of outdoor air is being introduced into the system. Unless otherwise required by safety or the specific project criteria, automatic dampers shall fail open for return air and fail to a minimum setting for outside air. HVAC systems shall be provided with automatic controls which will allow systems to be operated to conserve energy. The following energy-saving controls will be considered if applicable to the system. Enthalpy-controlled economizer cycle, controls to close outside air supply when the facility is unoccupied. This would be for non-laboratory areas only. Night setback controls where appropriate. Master outdoor temperature sensing unit that resets the supply hot water temperature in accordance with outdoor ambient temperature. This sensing unit shall automatically shut off the heating system and the circulating pumps when the outdoor temperature reaches 65 degrees Fahrenheit unless needed for special research purposes. Controls to shut off exhaust fans where appropriate. Reset controls for hot and cold decks on air conditioning systems having hot and cold decks. Automatic air control dampers must be of the low leakage type with a maximum leakage of 6 CFM per square foot at a maximum system velocity of 1,500 feet per minute and a 1-inch pressure differential as stipulated in AMCA Air Movement and Control Association Standard 500. The dampers shall be opposed blade type for modulating control but may be parallel blade type for 2-position control. Pilot positioners and operators shall be out of the airstream. Variable air volume VAV systems shall be designed with control devices that sense ductwork static air pressure and velocity air pressure and control supply fan airflow and static pressure output through modulation of variable inlet vanes, inlet discharge dampers, scroll dampers, bypass dampers, variable pitch blades, or variable frequency electric drive controllers as described in ASHRAE Handbook, Applications Handbook, Chapter 41, and ASHRAE Systems and Equipment Handbook, Chapter 18. These control systems shall have a minimum of 1 static pressure sensor mounted in ductwork downstream of the fan and 1 static pressure controller to vary fan output through either the inlet vane, the damper, the belt modulator, or the speed control. Exhaust fans, supply fans, and return or relief fans shall have devices that control the operation of the fans to monitor air volumes and maintain fixed minimum outdoor air ventilation requirements. All air handling systems shall be provided with smoke and fire protection controls required by NFPA 72. All supply, return, relief, and exhaust air ventilation systems shall have interlock controls that interface with the fire and smoke detection system controls. In the event of fire, these interlock controls shall either turn off or selectively operate fans and dampers to prevent the spread of smoke and fire through the building. These controls shall comply with NFPA 90A. Special exhaust systems shall be designed to include fire and smoke safety controls as required by NFPA 91. Kitchen exhaust ductwork systems shall be designed to include all fire and smoke safety controls as required by NFPA 96. Engineered smoke pressurization and evacuation systems shall comply with the following: NFPA 72, NFPA 90A and 92A, ASHRAE Manual, Design of Smoke Control Systems for Buildings, and ASHRAE Handbook of HVAC Systems and Equipment. Gas-fired air handling units shall be equipped with operating limit, safety control, and combustion control systems. Gas burner and combustion control shall comply with factory mutual loss prevention data sheets and be listed in the FM approval guide. Gas-fired air handling units shall have controls that lock out the gas supply in the following conditions: main or pilot flame failure, unsafe discharge temperature, high limit, high or low gas pressure, no proof of airflow over heat exchanger, combustion air loss, loss of control system actuating energy. For cooling towers and water-cooled condenser systems, controls for cooling towers shall conform to NFPA 214, standard on water cooling towers. Design of cooling tower fans shall consider use of variable speed drives if feasible, or two-speed motors if feasible, and on-off controls to reduce power consumption and maintain condenser water temperature. Bypass valve control shall be provided if required to mix cooling tower water with condenser water in order to maintain the temperature of entering condenser water at the low limit. To decrease compressor energy use, condenser water temperature shall be allowed to float as long as the temperature remains above the lower limit required by the chiller. The design shall provide basin temperature sensing devices, and if the cooling tower is operated under freezing conditions, shall provide additional heat and control system components to maintain cooling tower sump water temperatures above freezing. When appropriate, additional controls and sensors may be added to the condenser water system to provide condenser water to laboratory equipment that may require it. In addition, provisions for supplying emergency condenser water to laboratory equipment may be required. The entire control system shall be connected to the Central Control and Monitoring System, CCMS, network. The VAV controllers shall be fully compatible with the CCMS, allowing complete monitoring, control, and set point adjustment of all VAV terminal unit controllers from the CCMS host. One personal computer must be provided for monitoring, controlling, and resetting of any control device in the complex. This computer shall also serve as the connection through a modem to a CCMS. A minimum of one laptop computer shall also be provided for use as a field interface device to monitor, control, and reset any applicable point for any control device. The supplier of the control system shall provide 3 copies of the operating software, 1 copy on the central control computer and 2 sets on CDs or similar storage unit, and 3 sets of technical manuals for the control system. This system must be expandable to include the future phases. All utilities, including electric, gas, oil, and potable water utilities to be monitored, shall be metered and tracked by the Central Control and Monitoring System, CCMS. All meters shall be compatible with the installed controller system, shall be provided with signaling devices, and shall fully interface with the building HVAC control panel. Submetering of utilities to various buildings or equipment shall be based on project criteria, or in the absence of these, on sound engineering judgment. Submetering of lighting systems shall also be considered. Units of the same type of DDC equipment shall be products of a single manufacturer. Each major component of equipment shall have the manufacturer's name and address and the model and serial number in a conspicuous place. Materials and equipment shall be standard products of a manufacturer regularly engaged in the manufacturing of such products, which are of a similar material design and workmanship. The standard product shall have been in a satisfactory commercial or industrial use for 2 years prior to use on a project. The 2 years use shall include applications of equipment and materials under similar circumstances and of similar size. The 2 years experience shall be satisfactorily completed by a product which has been sold or is offered for sale on the commercial market through advertisements, manufacturers' catalogs, or brochures. Products having less than a 2-year field service record will be acceptable if a certified record of satisfactory field operation for not less than 6,000 hours, exclusive of the manufacturer's factory tests, can be shown. The equipment items shall be supported by a service organization. Items of the same type and purpose shall be identical, including equipment, assemblies, parts, and components. A portable workstation tester shall be a Dell Inspiron 2600 or equivalent, if it shall include carrying case, extra battery, charger, and a compatible network adapter. The workstation tester shall run DDC diagnostics, load all DDC memory resident programs and information, including parameters and constraints, display any point in engineering units for analog points or status for digital points, control any analog output or digital output, provide an operator interface contingent on password level, allowing the operator to use full English language words and acronyms, or an object-oriented graphical user interface, display database parameters, modify database parameters, accept DDC software and information for subsequent loading into a specific DDC, provide all necessary software and hardware required to support this function, including an ANSI 232F port. Disable and enable each DDC and perform all workstation functions as specified. The central workstation tester shall be a Dell Dimension 4500 or equivalent. The central workstation tester shall run DDC diagnostics, load all DDC memory resident programs and information, including parameters and constraints, display any point in engineering units for analog points or status for digital points, control any AO or DO, analog output, digital output, provide an operator interface contingent on password level, allowing the operator to use full English language words and acronyms, or an object-oriented graphical user interface. Display database parameters, modify database parameters, accept DDC software and information for subsequent loading into a specific DDC, provide all necessary software and hardware required to support this function, including an ANSI 232F port. Disable, enable each DDC and perform all workstation functions as specified. Installation of wireless sensor technology should be considered for control metering and monitoring devices. The primary components of a wireless sensor data acquisition system include sensors, signal conditioners, transmitters, repeaters, optional, at least one receiver, a computer if data processing is planned, and connections for external communications to users such as building operators. Depending on the specific application of wireless sensors, the following table may be used. This table indicates the application, power source, frequency band, communications and topology, maximum range, and typical cost in 2006 dollars. And slide 37 provides a continuation of the table that began on slide 36. For each project, the implementation of wireless sensor technology will depend on the determination of economic cost effectiveness of the wireless data acquisition system. All DDC software shall be furnished as part of the complete DDC system. Updates to the software shall be provided for system operating and applications software, and operation in the system shall be verified. Updates shall be incorporated into operations and maintenance manuals and software documentation. There shall be at least one scheduled update near the end of the first year's warranty period, at which time the latest released version of the contractor's software shall be installed and validated. And this brings us to the conclusion of this brief discussion of energy efficient controls for HVAC systems. I hope that this was about what you were looking for, and that this information has been somewhat helpful to you and will allow you to address projects of this type that come across your desk in the future. So again, thanks a lot for letting me chat with you, and have a nice rest of the day.